Hello, everyone, and welcome to the Geek Nighter podcast. I am your host, Keval Yapte. This is another episode on databases, but today we are not going to talk about any specific database internals like we usually do, but we are going to talk about database optimizations and tunings. And as you all know, that databases are complex, and running databases in production, serving real customers, tons of data, tons of traffic is even harder. And it gets harder when you have to tune that database for specific workloads. So today I have Andy Pavlo with me, who is an associate professor at CMU and also the CEO and co-founder of a database tuning startup called Ottertune. So we are going to talk about database optimizations and Ottertune and how all that works. So I'm really excited, Andy, to have you here. Welcome to the
Hey, thanks
show.
for, thanks for having me.
Yeah, let's start with a little bit of introduction.
Yeah, so as you said, I am an associate professor with indefinite tenure. Actually, my official title is associate professor with indefinite tenure of databaseology in the computer science department at Carnegie Mellon University. That's my official academic title. But I'm also the CEO and co-founder of Ottertune, as you said, is a sort of automated database tuning startup that I spun out at the university with two of my students, Dana Van Aken, who was a PhD student with me at Carnegie Mellon, and then Bohan Zhang was a master's student at Carnegie Mellon.
Awesome. Um, I typically start, to make it beginner friendly, I start with very basic and to make sure everyone understand what we are going to talk about. And I'm sure we are going to talk about more advanced topics as well. Let's start with, setting up the context here. Like, what do we mean by database optimization? And, is it only about optimizing databases for improving application performance, or there are other dimensions to it as well?
Yeah, so databases are an interesting category of software because they are designed to be this sort of most systems are designed to be general purpose, meaning if you have an application that's for a university or application for a bank or an application for a social media website, you can load those things into or set those things up in a database system. And it's designed to accommodate all of them. So you can define your schema, you can define your queries, and the database system has to sort of support all of them. And so the reason why you have to optimize these systems is because since it's general purpose, the default settings for that the system uses may not be the best for for your application, like sort of like the lowest common denominator. And then there's further assumptions you have to make about the hardware in these systems that again may not suit the environment that you're running on. And so the idea is that you could think of a database system as the metaphor I like to use is like the database system, something like Postgres, MySQL, Mongo, Oracle, whatever. You could sort of think of it as like a general purpose generic car frame. And so if you want to make a race car, well, you can put a big engine in it and make it run fast around the track. Or if you want to haul big loads, you put big tires on it and make it look like a pickup truck. Like the core frame is essentially still the same. So that's what database optimization basically is. It's like you're tuning these knobs, tuning different parameters, changing the physical schema of the database, changing how it's actually storing the data, how it actually wants to execute queries. And we'll go through all of these examples. Like you modify those things in such a way that's tailored for the application that's running on it. So if you're running on a social media website, you maybe want to tune the database system one way. If you're running a bank, the workload looks differently, and you want to tune it another way. So at a high level, that's the idea.
Yeah, that makes sense. And but what makes database optimization so difficult? And I understand that it's workload specific, and there's a lot of specific tuning that you might have to do. But what is that reason? Like, what makes it so difficult that people often get it wrong?
Yeah, because it's hard because database systems have a lot of options, have a lot of different ways you can tune them. And I would say this is not a new problem. Like this goes back to actually the 1970s. So when people were building, say, the first databases, even the first relational databases, there was a lot of early discussions about, okay, well, a lot of the low level details of the system of how the database system is going to store the data and run queries is abstracted away from the application developer. Someone's going to need to come in and actually set this thing up correctly. And so there's been a long history, decades of work try to automate this to help humans deal with this.
Hmm?
So the reason why it's hard is, as I said, database systems are complex pieces of software. It has a lot of moving parts. It's you're storing a lot, potentially large amount of data, trying to run a lot of different queries, and understanding how the database system is going to interact with your application and the hardware, because it sort of sits in between the two of them, is non-trivial. It's a very challenging problem.
Yeah, absolutely. Um, I mean, there are different areas you can tune your database performance. There is query performance, there is index, there is partitioning, also related to hardware, right? And there are some, other tuning options. Um, w- w- so let's say I have a very simple workload, right? And I am using, let's say, Postgres database. When do I know that I need some kind of tuning? What are the, sort of indicators that might show me that, okay, this needs tuning now, or the default is good enough?
So I would say let's go by the category of what these you can tune. And in general, I like to say there's sort of four rough categories, right? Of things you can tune in a database system. So the first one would be the physical design. So this would be how the database system is actually storing the bits of your data on disk or in memory. And this would include things like what the data structures it would possibly use for index, whether it's a row store or a column store, whether you use compression, whether you use partitioning, as you mentioned, right? It's the physical layout of the database system itself. You could probably also include in that, normalization and denormalization of the table schema as well. The next one would be configuration tuning, or parameter tuning, or knob tuning. And these are these parameters the data system exposes to you that allows you to change how much memory to allocate for the buffer pool, how much memory to allocate when you're doing a join or doing sorting, or when to write things to disk. Like this control the behavior of the system as it executes queries. The next one would be query tuning. So this would be influence the database system on how it's going to execute your query. And this is primarily an issue especially in relational databases, or any database system that exposes a declarative query language like SQL. And there's other variations of this, but like it's where you're not telling the data system how to execute your query, just telling it the answer you want. And now the data system has to convert that SQL statement, for example, into a query plan and execute it. So you can tune how it actually wants, how it actually will generate that query plan in some ways that could make it more efficient, like how to join tables, in what order, whether you use an index or not, things like that. And the last one would be hardware provisioning or resource provisioning. And this is deciding that, okay, well, I've done all the other tuning, and I don't have enough memory to keep my working set in the buffer, or the disk is real slow, so I'll upgrade the disk or add more CPUs, right? That one that one's probably the hardest one. And that one, I don't think there's actually really good research in this area. So we can put that one aside. I can talk a little more about it if you want, but let's focus on the first three. So typically what happens is that people, there isn't there isn't like a single metric that someone could use and say, a giant red button on your data, or red flashing light in your database that says, hey, this is too slow, fix it, right? It's very subjective. And because it depends on externalities or external factors that the database system can't know about. So again, if you're like a social media website, you want to be able to load your pages in, tens of milliseconds. But if it's like a backend batch processing system, then like, who cares if your query maybe takes, 500 milliseconds, because no human's waiting for that. So, it's hard for me to say, okay, like this is the one thing. If you see this, yeah, stop what you're doing and go tune it right away. I'm going to say also too, though, typically what we see in the real world is that tuning is sort of an incremental or iterative process. It's not like you just stop all application development typically and just like do nothing but tuning. It's usually like, okay, well, this one query ran a little slower than I wanted, and someone's complaining. Let me go speed that up. Or we're running out of disk space, and again, ignoring that you can scale things out in the cloud, but like you're running out of disk space. Can we use compression to reduce that, right? So I would say that the typical thing that we see is that people feel or think that their queries are running slower than they actually should. Um, and it's actually inhibiting them from, uh, getting work done or, supporting the customer's needs with their application. So the, and I would say also too, it depends on the workload. So as I said, if it's a front end application, like a social media website or anything that users are interacting with the application, then you want those latencies to be as low as possible. And the general rule of thumb is that you want your transaction completion time to be under 50 milliseconds. It could be multiple queries within that time or a single query. If you get that, then that's okay. For the sort of analytical workloads, again, it depends on the needs, depends on who's actually running the query. Like a dashboard, you want something like come back right away because people are going to think that the application is broken if the query takes minutes. But if it's like end of the day reporting where no one's going to read the result of the query until like the next morning at 8 a.m., then okay, if it takes a little longer, who cares? So again, I would say query latency is probably the number one thing that people, identify like, okay, yes, I need to do some tuning. But there's other factors like cost, right? If you feel like that the data set is costing you too much money, can you optimize it and then have you downsize the resources or use less disk or less IOPS, depending on the pricing model of your databases. So there's a lot of different factors involved. But again, latency is typically the biggest one.
Yeah, absolutely. And, as you mentioned, if you're supporting a customer facing application where some things are really, time sensitive and, latency sensitive, then I guess understanding the SLOs of, what your objectives are for that particular operation. And if database is becoming a bottleneck, I think that can be a good indicator of, that you need some tuning. And also
I would say
depending on,
the one thing that surprised me, sorry to interrupt, is like people don't have SLOs, right? Like, there'll be some number that's given sometimes, but like, if you're dealing with sort of major corporate enterprise contracts, there might be something in place. But for most startups, most people, it's like, it feels slow, but they can't quantify a number on it.
Yeah. And for many of them, just default settings also work. They just try to kind of, for example, if it's a read heavy system, people tend to have read replicas to just scale the reads and, those kind of, let's say, I don't want to call it workaround, but they are workaround in a way where people, if they have, some, let's say, budget in terms of cost or some, understanding of how the read replicas work, they just try to, optimize or, scale in that way. But maybe there are better ways of tuning on a single machine as well. And for that, I guess it requires a good understanding of a database, like how things are working internally at all levels, right? Like starting from writing the API writing the queries till how, buffer pool and, other things are configured, or till what kind of hardware is required. So I guess it requires that kind of expertise. And I guess given how the industry has changed from last decade, I think that expertise has somewhere lost, right? Because we don't. So I typically used to work with DBAs a lot like 10 years ago, but now I don't know if there is any DBA. At least that title. There are some folks who have like experience working with databases, but I don't know if they are DBAs, right? So that could be another reason, right?
Yeah. So I don't have numbers on this, but I agree that the seems to be that the role of the DBA has diminished. And a lot of times, again, this is speaking in terms of like the startup, the bigger enterprises that we talk to will typically sometimes have DBAs. Think of like more traditional, like, brick and mortar kind of companies, Fortune 500 things. The tech companies less so, right?
Mm-hmm.
And so I think that even if you had DBAs, I think I think that it's not realistic to assume that a human's going to be able to manage and tune these databases. Because not only is just a single node, single database by itself is complex enough, but like now that it's not uncommon for companies to have tens, even hundreds of databases. And it's not realistic to say, okay, I'm going to have, a human manage like all 100 of them. It's like not realistic. So, and this sort of gets into, what we'll talk about is like automation is the key for this. So like, even if it's one database, that's hard. Now, if you scale out, humans are expensive. And you're basically paying someone to babysit software and manage it.
Mhm.
And I don't think it's the best use of somebody's time, because there's other high level things that DBA could actually be working on and helping out.
That makes sense. Um, so I guess, and again, I'm assuming, and based on my limited experience, that the default settings would just work fine for a lot of those workloads, right? And I mean, fine as in if they don't have SLOs and they say, okay, it's fast enough, right? So they don't have a good way of measuring it. It might not be the best possible optimization that they have done, but it seems to work because users are not complaining, they don't have errors or something like that. um, and then there could be some specific types of workloads, let's say read heavy, write heavy, delete heavy, different types of workloads that might need some specific optimizations. um, is it also depending on the vendor or the type of database, or what other parameters does it depend on?
Yeah. So let's talk about what we mean by the default first. And so typically the default settings would be referring to the knob tuning or the configuration tuning, because these systems have to
Mm.
ship with some default configuration. And then typically it's related to query tuning too, because you're not trying to, you're not giving hints to the data systems optimizer to the query a certain way.
Yeah.
I guess for physical design as well, this is the case. So let's go through each of them one by one. So let's start with the physical design. Um, for some systems, especially more the enterprise systems, so like the Oracles, the SQL servers, DB2s, there's way more things you can tune in the physical design. And typically, if someone's paying a lot of money for like Oracle or SQL Server, like it does make sense to pay all that money and then not actually do any tuning. The default settings aren't going to be, they'll be maybe okay, but like if someone's paying a lot of money for Oracle, they're not going to run with the default. It sort of would be crazy. For things like indexes, typically those get created automatically for our foreign keys and primary keys, and that might be good enough for most of the queries. You typically want to start doing index tuning when when your queries are sort of running slower, because there's a trade-off of like if you add too many indexes, that makes updates slower. So there's a balance there. For knob tuning, the defaults are, I think for almost all systems, are woefully insufficient. Especially MySQL and Postgres, they're actually really bad. Now, if you run on like a managed service like RDS or Azure or Cloud SQL, they've done some tuning for you, but it's like the lowest common denominator. It's pretty generic. And further tuning can beat them by a factor of 2x in some cases. For provisioning, that's interesting because there's some systems that can have sort of automatic scalability. You typically see this in the OLAP world. We can say, automatically give me more CPUs, like Snowflake can do sort of stuff like this. And that helps, sort of automatically scale your database data warehouse over time as the workload changes. But for other things like again, running Postgres MySQL in a managed service, in those environments, it's a hard decision to say, I need to upgrade or downgrade my instance size. So I would say, like, I think it's probably more common, but I can't prove this, that for the open source databases, the Postgres, MySQLs, and others like that people are more likely just to use the default. And then if things get bad, then they start tuning. For the enterprise systems, because again, they're so expensive, I'm pretty sure that most people, like, if you're paying for a SQL server, you must note something about what you're doing, or recognize that you should be actually tuning this because it affects the cost. And they probably just, I would not be surprised if most of the systems are not running the default configuration. Now, it's the Oracle and SQL Server, they have other built-in tools to do some automatic tuning for certain things, but not all the things that I mentioned before. But again, like, it's like if the default is, if you're not stressing the data system, the default is might be okay. But I would say the mistake that we see people make, I'm biased also too, because I'm trying to sell a service that does this tuning for you. The mistake that we see is that people don't do any tuning, especially in RDS. And when queries run slow, they just bump up the instance size. So they'll pay Amazon more to get more CPU and more memory. Where in some cases, actually, it makes sense to tune what you have now, because that might get you, buy you more time and make better use of the hardware you're already paying for before paying extra to go to a larger instance size.
Yeah, that makes sense. Um, does it also depend on the type of database? Like we have this, broad classification of database, right? Like SQL databases and NoSQL databases. Is it also that complicated when it comes to NoSQL databases, or there are so many tunings there as well?
Well, with the NoSQL guys, they all support SQL now, right? So it's not
Yeah,
really a unique distinction, at least in
yeah,
the name, right? Cassandra supports SQL, or they call it CQL.
SQL,
Uh,
yeah,
Mongo, again, for the longest time, I've known the co-founder of Mongo, and he told me in like 2012, in their headquarters in New York City, he's like, "Oh, Mongo is never going to support SQL." And then 2021, although after he left, 2021 they added SQL, right? So I don't think there's. I would say there's all the things that I mentioned before, with the exception of maybe query tuning, because if they don't expose plan hints, so they don't expose they don't have a real cost-based optimizer and can do joins, then yeah, it doesn't. There's nothing really to tune on the query itself. But
yeah,
for all the things that I mentioned before, all these problems exist in no matter what's NoSQL or SQL, and whether it's like an operational database, like a front-end application, or like a back-end data warehouse doing analytics. Um, all the things that I mentioned, these are all considerations that everyone has to deal with. Now, it depends on whether they expose the capability for you to do this tuning. And this is typically, issue in the cloud, right? So Snowflake, for example, I know they have knobs on the inside to tune the system, because they told me they have them. It was like, at the time, it was like 500, 600 of them. But you as the user, there's only like 2 or 3 of them that you can actually tune. And it's like, I think it's like the scale factor, like whether you want to scale up or not. And that's it. But like all the things you can tune in like Postgres and MySQL and other systems, you can't even touch in Snowflake, because that's all hidden from you.
yeah.
So whether or not like you can tune everything that we've been talking about depends on whether the service provider exposes it to you. But I would say, again, it doesn't matter whether it's a back end or front end application, you want to do these things.
Yeah, that makes sense. Um, Given that it's so complicated, let's understand how machine learning can help here, right? And how Ottertune can help. So, what is Ottertune, first of all, and how does it help in tuning?
Yeah. So actually, before we jump into that, let's talk about like sort of the history of sort of database tuning, at least in automated database tuning. Because I think, as I said, this has been an old problem. Like my PhD advisor, his PhD advisor wrote one of the first papers on automated index tuning in like 1976. So people have been trying to do this for a long time. And then in the early 2000s, late 90s, Microsoft was really, really pushing this effort in the AutoAdmit project out of Microsoft Research. They did a lot of early pioneering work on this. So people have known that this is a problem and have tried to come up with ways to help people deal with this. But what has sort of changed in the last 10 years is that a lot of that groundbreaking work in the 2000s from Microsoft, Oracle, and IBM had similar things. They were all sort of recommendation tools for a human DBA, meaning you would run this tool and it would say, "Hey, you're missing these indexes," but then a human had to come and click, say, "Yes, yes, yes, install," right? And we're sort of at the current era now where we're trying to apply machine learning or AI methods to database optimization and completely automate all of this, right? Because again, if you think you have tens or hundreds of databases, no human can sit and go, "Yes, yes, yes," all these things. This is just not feasible. So with Ottertune, this is a project that we started actually in 2013 when my very first year at Carnegie Mellon as a new professor. And I was looking at how to apply machine learning to do database optimization. And my PhD thesis included some work on automated methods to optimize a particular system called HStore. It's been commercialized as VoltDB, but we were sort of looking at how to do automatic partitioning and other tricks with transactions. And the challenge I was facing as a student at the time was it was impossible for me to get real workloads, real customer traces, real databases to actually try my methods out. So with Ottertune, I was looking at what's the problem we could solve in database optimization that didn't require us to actually get real workloads and traces? Could we still provide the benefit of automated tuning without having those things? And so the target space was configuration tuning, or the knob tuning stuff. And the original thesis idea was, could we apply machine learning to automatically tune the knobs of a database system by just looking at the internal telemetry or metrics that the database system is generating, without actually having to see the SQL queries and actually having to see the real database? So this telemetry would be things like pages read, pages written, locks held, like all these internal counters that the database system maintains about what it does when it executes queries. Every database system maintains these things because they're meant for DBAs to understand what's going on and why queries are running slow. So if you're using Postgres, this would be like in pgstat statements. If you're using MySQL, you can go show InnoDB stats or look at the performance schema table. It'll show all these things. So it's all this benign information about the internals of the system. And the idea with Ottertune was, can we suck that information out, get an idea of how the application is actually using the database, and then use machine learning to automatically tune the knobs. And so we had an early prototype in 2013. And then again, my co-founder at Ottertune, Dana Van Aken, she started as a new PhD student with me, I think in 2015. We started building like a more fleshed out and thought through like prototype. And the initial version worked really, really well. We compared it against sort of other configuration tools at the time, like pgtune is a popular one people use, or MySQL Tuner. And these are just rule-based tuning scripts, which is representative of what people did in the 2000s. And what we showed is that you can actually learn from tuning one database, if you have some Postgres database, you tune that. And if someone comes along with a new Postgres database you've never seen before, but it looks very similar based on those workload metrics, like what the queries are actually doing, could you apply the knowledge you gain from tuning the first database to tune this new database you've never seen before? And it works. And so we published a paper in a research conference, the top database research conference in 2017, 2018. And when it came out, the other academics were like, oh, great, this seems kind of cute. But then we actually got invited to write a guest blog article for the new Amazon AI blog, which is just a summary of the original research paper. And we did this because Amazon gave us research credits to run our experiments on EC2 for the paper. And when that blog article got published, we had a bunch of people reach out to us and say, we have this exact problem. We'll give you money to fly a student out and set up Ottertune for us. And we're like, oh, okay, well, this seems to be a reoccurring theme here. Maybe there's a startup. And so in 2020, when Dana was finishing her PhD, just about to defend, so we decided to spin it out. And we brought in a master student, Bohan Zhang, that worked with us on an early prototype. He was a co-founder with us. So the original academic version of Ottertune was doing just knob tuning. And since then, in the commercial version, we have expanded it to do some basic query tuning and SQL checks, or SQL tuning, or sorry, index tuning. But we find that most of our core customers are coming to us for the knob tuning capabilities.
Okay. Interesting. So, so you briefly mentioned like what kind of data is collected to kind of give as or feed into the machine learning model, and then get the recommendations back. What other data is collected, and how the data is collected? What that process looks like?
Yeah. So to go through the three categories: knob tuning, index tuning, and query tuning, SQL tuning. For knob tuning, it's the internal telemetry that the data system generates. But we also collect sort of hardware metrics from the service provider. So right now, Ottertune only supports Amazon RDS. So in AWS, there's this thing called CloudWatch, and that gives like hypervisor stats. So like CPU utilization, memory usage, disk IOPS, and things like that. So we collect that as well. For the index tuning, it's a combination of internal telemetry from the database system about how indexes are being used, but you also need the schema from the database as well. And so, because like, we recommend that we identify like, whether there's duplicate indexes or unused indexes. And so if a table, if a table has a primary key has to have an index in order to enforce it. We don't want to tell you to drop the primary key index, right? Because then you have to change a bunch of changes of the application. It's a huge pain. So you need some schema information to understand the context of some of the recommendations that you're making. Same thing for the query tuning. I have to admit, our query tuning is not as good as it could be. And this is a limitation of the data that we can collect. So right now we only collect the SQL string itself of, from either from Amazon or from the database system. And so we don't actually know what the query plan is. So our current version of our SQL recommendations are looking for Andy patterns, things where that you write a query a certain way, that the database system is just going to choke on it and generate a bad query plan and run slowly. So there's some checks we can do to say, hey, look, this is not the right way to write the SQL query. Here's a better way to do it. The big goal would actually start connecting to the database, trying out SQL queries to see what the plan is. And you can do this in most databases using the explain keyword. So any query you have, you put explain in front of it, and it'll give you the query plan without actually running the query. So you can use that to figure out, okay, what is the database actually going to do if it runs this query again? And then you can use that to guide the recommendations accordingly.
Interesting. And do you also give recommendations on the data model itself, like how the tables should be structured and all of that?
Yeah, not yet. Okay. So this would be like schema recommendations. Yeah. And I would say there's two versions of it. There's the first version that we're working on now is to be able to do recommendations for similar to like the SQL queries, like Andy patterns. So these were things where that someone has made a mistake and just defining defining certain things in the schema. So an example would be, if you have a table in Postgres with the name of the column is like something like IP address, but then they're storing the data type, the value of that attribute in the table is a varchar, so a string. Then that's not the most efficient way to do it because there's actually a native IP address type in Postgres, and you should be using that. Same things with UUIDs. There's other things like that. So there's recommendations like that we can start doing because we collect the schema. To do refactoring of the table schema itself, like deciding that you want to break up two tables or combine them. So normalize or denormalize is the sort of the academic term of this approach. The reason why we don't go down that path is because it's very unlikely that anybody would actually apply our recommendations because it'd be a major, major change to the application code, right? Because again, most people aren't writing raw SQL queries. Most people are using like an ORM, an object relational mapper. So things like Hibernate, if you're using Django, they have active record. Ruby on Rails has certain things, SQLize, Node has a bunch of stuff. Like there's a bunch of these ORMs, and most people interact with the database through that. So now if you come and say, hey, these two tables should be split up, but now you got to say, okay, you got to then provide them like, here's the code to actually that rewrites your SQL or sort of rewrites your application code to break that table apart. But then that's going to break everything else in the application. So it becomes a nightmare. And so we have had discussions with major cloud vendors or people that you might, your listeners would definitely be familiar with about going up that stack and understanding how the application is actually being written in GitHub or Visual Studio or whatever, and then start making those kind of recommendations and getting them through like something like Copilot, the refactored version of it to make things faster. But that's a major, major undertaking that we're not something that we can pursue right now. But that's sort of the big challenge that we face in some of these recommendations. The SQL queries is another one. Like we can tell you, here's all the things you got to fix. But if you have to like make major changes to your application code, nobody's going to do that. And the nice thing about knob tuning is that like, again, you don't have to make any changes to the application code because it's just changing how the data system is going to run your queries or store your data. Some things with the schema stuff, you can get away with that too. Again, having to make any application code changes. But once you start saying things like, hey, you rewrite your application code to get this benefit, unless it's like such a compelling win for them, that's worth the time to actually apply the change. Nobody's going to do that. And everyone's just going to say, all right, well, yeah, I'm running slower, but I don't want to make the change you're recommending because I have to write code or change my code. I'm just going to bump up my instance size and pay Amazon more money.
That makes sense. It's a trade-off, and by the time they, even if they agree to change the application code, and by the time they do that, things might have changed, right? And there might be some new recommendations. Features are added to the product, and there is a ton of things happening. So yeah, it's very challenging.
Yes.
Cool. So from the deployment perspective, right, like how the data is collected, what exactly is deployed on my database cluster, for example, and how it is sent to the machine learning model.
Yeah. So we based our Ottertune's approach very similar to Datadog. So the way it works is you give us permissions on AWS to connect to your RDS accounts. And that just allows us to see what databases you actually have and get some basic telemetry for something like CloudWatch. But at that point, we obviously can't log in and get any data or access to the database. So then you have to download this Docker file agent. We have a Terraform script or CloudFormation scripts that help you do this. But it's basically a little Python code that just gets permissions to connect to the database and then scrape out all the additional metrics that we actually do need. And then we ship that back to our service. We also now support the ability to have that agent just write to an S3 bucket you then give us permissions to read from, because some companies don't want to poke a hole through the firewall to send us back information. And then so that once we have it on our side, we store this in a database. We use Postgres, and then we have a backend compute engine that then trains the machine learning models to based on the data we've collected, and then starts generating the recommendations to you. And you can either go through the web interface and see the recommendations that we have now. Like a REST API allows you to get the recommendations and decide what to do with them. So to apply the recommendations, the only ones that we can apply automatically is for the knob tuning stuff. As I said before, like we don't have the permissions to drop indexes or change the physical design of the database, because that's a major undertaking. You just don't want to do that automatically without people knowing it. And then same with SQL queries. Like we can recommend them, but someone has to change the code actually to deal with them. But we can apply the changes automatically for knob tuning because at least in AWS, they have a standardized API through RDS that you can apply the changes. They call them parameter groups instead of knobs. So some people want us to do that automatically. Other people still want a human to be able to approve, decide what changes they actually want to make. And again, this can either be done through the service or through like an external thing. Like you could download through the API our recommendations and then apply them to your own local Terraform files and install them.
Does it also give me an idea of, or an estimate of, how much performance gain I'll get out of it, or how much cost will be saved, something like that?
We don't do that now. We don't do. I fully admit we don't do a good job of this. We want to do better. So how to say this? The model at the very beginning, at least, it doesn't fully understand how your database is actually, what it's actually doing. So we don't want to say like, hey, you're going to get 80% improvement in latency like out of the box, because like, what if we're wrong? And then people get mad, right? In general, we see that people do actually get, if they've done, if there's things actually to tune, which is another challenge we face as well. Like if they've already done some tuning, then we may not always be able to get most of the benefit, right? We still be humans. We like in some cases, like we actually do quite well, and it's usually like 80%, and that takes roughly 1 to 2 weeks. So I would say one of the challenges we face that you brought up is that we don't do a good job exposing or giving or providing hints or letting users anticipate when things are actually going to change and when they're going to, what the benefit they could actually be getting. The challenge of part of this is that we have designed the service with the assumption that we're running on production databases. And therefore, we got to be very conservative about how we apply those changes. And so I said, like, it sometimes takes a week or 2 weeks to get the full benefit, at least just for knob tuning. That's because we don't want to be making changes, within, the first hour of seeing the database, because we need to see more information in order to guide machine learning models in the right direction. And obviously, like, you don't want to tune your database for, someone signs up on a Saturday but the majority of the workload happens between Monday and Friday. We don't want to start tuning our database on what we see on Saturday because it's going to be ill prepared for the upcoming week. So we automatically skip weekends and holidays. Like there's a bunch of stuff we have to do because we know we're running on production databases. Where we want to go to start solving the problem that you brought up, and we actually are rolling out a feature in this in a week or two, although it's the holidays, probably early next year, is that we can start giving hints and guidance of how somebody's database looks compared to other databases. So again, people, as you said, like whether they're DBAs or not, like they maybe only know just the databases that they're managing. But Ottertune sees lots of databases. And so now we can start giving them context about, hey, your database has high C utilization, and that seems unusual for what your workload looks like for other Postgres databases. So what we want to start doing now, in addition to giving sort of timelines of here's how long it takes for Ottertune for the models to converge, and say here's the benefit you're going to get, at least some prediction of that. We also want to be able to say that here's the things you should be tuning, and oh, by the way, 90% of the other Postgres databases that tune a similar thing got this kind of benefit. Again, just providing them with more reassurances that it's not, we're making recommendations not because Andy's the database professor or we read the textbook or whatever. It's actually it's driven by the data that we're collecting and the things we're seeing. And what's exciting about that is we can start using the same models and capabilities to start making recommendations for other things beyond knob tuning about just like the life cycle of databases. So people have asked us like, hey, what happens if I upgrade from like Postgres 12 to Postgres 13? So Postgres is the one we want to focus on here because in the last 10 years, they've changed their release cadence. So they're putting out a new version of Postgres every year, which is amazing. MySQL is still 8.0 and 5.7 or 5.8 are still they're still just making minor iterations of that. And so people ask us like, if I'm running on Postgres 12, what will happen if I upgrade to Postgres 14, 15, or 16? And so now you can start doing things like, okay, well, your workload looks like this. And we've seen other databases, Postgres databases, go through the same transition. And so when they upgraded, they saw this benefit or this degradation or this aspect change in their environment. So that's the other kind of hints we can start doing for the same kind of thing. And then you can apply it also for provisioning recommendations. Like your workload looks like this. Other databases that look like yours, they see this benefit or they see these kind of performance numbers on a larger instance size or a lower instance size. And that provides them more guidance about how to make smarter decisions over the long-term period of their database.
That makes sense. And that sounds like, creating sort of personas of these database depending on the workloads, right? Like if your database fits this persona, this might suit you, right? Like this version, this setting. Are there use cases when people come to you even before going to production that, oh, we expect this kind of workload and there's like, we expect to grow this much in the coming year. What could be our like best possible, configuration to start with?
Yeah. So this goes back to what I was saying in the beginning, where like we use this telemetry to understand what the database system is actually doing. And so unless the database system is experiencing or actually doing that work, it's hard for us to be able to say, oh yeah, a year from now, you're going to be twice the size and twice the number of queries. Like it'd be hard to generate synthetic data to make something appear to be something that's not right now. And so this has come up in some conversations with some customers. And what we've told them is like, okay, well, turn on Ottertune and just leave it running. And then as your workload evolves and as the size of your database evolves or whatever changes you're making in the application, as those things change over time, then Ottertune will evolve with you. And I mean, that's sort of the right way to do this. I think that now, for gradual changes, this makes sense. If Tuesday, your database looks like this, and then Wednesday, it's completely different because you're running like, you were doing, I don't know, you're running some bank today, and then the same database next day is now running Twitter, like something completely different. Yeah. And like, there's like, Ottertune's not the best thing for that because that's a dramatic change. And from our perspective, it's a brand new database. But people don't write code like that, right? It's always like you put out the initial version, you start collecting some data, get some users, and then over time it gets bigger, add new features. And in that case, Ottertune can just march along with you and make changes and make recommendations as you go along. We think that's the best approach for this because that
Yeah.
fits how most people write code or write applications.
No, that does make sense. And so I've worked with some e-commerce companies where this Black Friday is a huge deal, and for, the rest of the year, it's totally fine. There's no, spiky behavior. But for Black Friday, they do like specific types of load testing and, resource provisioning and, all that kind of things. Um, how could, something like Autotune help in that kind of spiky behavior? Let's say not just Black Friday, but there are like 4 or 5 such events over the year where you see
Yeah.
really spiky behavior, but rest of it is totally fine.
So I would say there's 2 categories, right? There's the periodic spikes where it's going to be like the end of the month reporting, or like this day, or the second Friday or third Friday after Thanksgiving in the U.S. There's going to be a spike in traffic, and those things. The way we don't do this yet, but the way we want to handle that is have the ability to sort of save or bookmark, so to speak, a configuration. So then you can then put it on the schedule and say, okay, when it's this date, switch to this configuration, disable all other tuning because you want to reduce the amount of load. And then after the holidays or whatever, after the end of the month quarterly reports, switch back to like the regular day-to-day configuration. So we haven't done that yet. That's what we want to do. Another kind of event I would call black swan events, where it's not on a regular schedule. It's unexpected. All of a sudden, like whatever, your website makes front page of Hacker News or Reddit or whatever the hot social media website is. And all of a sudden you have a flood of traffic and things look, way worse than ever did before. And so again, admittedly, Ottertune doesn't handle that right now. Because I said, we're assuming you run a production database, and therefore we're not trying to make changes on a per minute, basis, because that would be where you would have potentially wild oscillations. So the way we want to handle this is basically have trigger events to then say, okay, like if I see my latency spike above some certain amount, or then the throughput goes above this, or something happens, that's an anomaly, and then have some logic that says, okay, should I have a pre-canned configuration that it is designed for that, or should I start tuning for within a very small time interval to handle that spike in traffic? That part we just haven't gotten yet, because oftentimes, as you said, like for these black swan events or major events, like we can do all the tuning we want, but if you're just saturating CPU, like because you're just under provisioned, you need to scale up. And as at the very beginning, you were talking about maybe offloading read-only queries to the read replicas. Again, we can't control that right now. So this has not come up. What we see typically people do is like, I know I'm going to be in the holiday period, have a lot of traffic, so let me just disable any Ottertune recommendations during that time, and just deal with whatever the best configuration I have. Last time I Ottertune ran, and then I'll re-enable tuning again in January.
That makes sense. I'm just curious how, things like these are tested, like when it comes to database, right? Like let's say Autotune recommends something, that this is the configuration, and, you do this and, expect this kind of performance gain because others are gaining. How are these things tested? Like there are 2 parts to it, right? Like one, how Autotune itself tests what it is generating, and how it expects users to test.
Yeah. So let's actually talk, before we get to testing, let's talk about like, what are the safeguards you actually have to put in place to have like a machine learning AI powered tuning tool for a database system,
Yeah.
right? And this actually goes back to when it was a university project. We made the assumption that, and this was very similar to other research papers, that nobody would run this on a production database. That you would take a snapshot of the database, spin up a clone machine, capture workload trace, and replay the workload on the side. So you can run repeatable experiments on the side and use that, you have a baseline to know whether you're, before you do any tuning, to know how much better or worse you're making the system. And when we were at the university, everyone we talked to that wanted to run Ottertune, the big banks, big brick and mortar companies, they all could do this, right? Because they had full-time DBAs. Then when we spun it off as a startup, we found out that like nobody can do this. Right? Like people can create snapshots because there's like in the case of RDS, there's a button just to do it. But the workload trace and replay, that's a bit complicated. And furthermore, the open source tools to do workload replay for Postgres and MySQL are nowhere near as sophisticated as the commercial ones, like for SQL Server and Oracle. And I'm assuming DB2 and others have similar things. So because of that, we had to then, say, okay, we assume that we're running in a production database, and therefore we got to put a bunch of guardrails to make sure Ottertune doesn't cause any data safety or integrity issues. So that means that we've had to basically manually curate what Ottertune is actually going to tune in terms of knobs to make sure that we don't end up tuning things that could cause you, if you crash, you could lose data. So the classic example I always like to use is there's knobs that tell the data system for Postgres, MySQL, and every system whether you want to flush the disk, the write-ahead log to disk when a transaction commits. And so you can turn that off. Basically say, okay, like everything just sits in memory. And so the machine learning models learn very quickly that if you don't write to disk, your database goes faster. So it always wants to tune that, right? And so, but that's a good example of like external costs. Like the machine learning models don't know, okay, if I crash and lose data, my business fails. So, people get pissed. It can't reason about these things because that's outside of its purview. So we've already done some curation to make sure that we only tune things that can, that we know that aren't going to affect, those kind of data safety issues or durability issues. There's other curation we've already done for identifying which knobs have the most impact. And so this one, the way you do this is we basically just ran a sweep of all possible parameters. I think Dana ran 100,000 experiments on EC2. And then you just do a factor analysis to say what knobs have the most impact on performance. And so we target those first. So like for Postgres MySQL, there's 10 knobs that we know that have the most impact. So we always recommend tuning them. And after 10, those knobs can have some benefit, but it depends on the workload. And so some people turn them on and they see some benefit, some they don't. But then for those knobs that we want to tune, we then constrain the machine learning models to only consider values within appropriate ranges. So obviously, if you're running on an instance or a machine that only has 16 gigs of RAM, it doesn't make sense to try your buffer pool. You set your buffer pool size to 1 terabyte, right? So we artificially limit the range in which the knobs can actually take, and that prevents again out of memory issues and other things like that. So that's what we had to do all ahead of time before we even get say now we want to run on production databases. So your question is, how do we actually test this thing? So we just run through a series of tests over and over again to make sure that for known workloads, that synthetic workloads that we have, we get the expected benefit that we would see, that we don't see, after 10 iterations or so many iterations of the machine learning models that they degrade inappropriately. And so there's a bunch of safety checks we've done for that kind of thing. For indexes and SQL tuning, again, because we're not applying this automatically, we just need to test that for known scenarios where an index is not being used, that we correctly identify that it's not being used. And then we can determine whether it's a foreign key or a primary key and avoid, tell people it's recommended to turn it off. Unique is another one too. A unique index is there's some external factor that a human decided that this should be this index has to exist and it's unique. We don't recommend that you drop it then.
Interesting. Yeah. That sounds very complicated. It's really hard to get it completely right, but I guess it will evolve, right? The model is evolving with more and more data.
Yes.
And is it the same model that works for all database vendors, or when you have to add new database to your service, do you have to tweak the model a bit?
So let's be very clear here. So there's the model instance, the thing that gets trained and generated, the weights and so forth. That's that's going to be specific to, Postgres and MySQL and whatever, right? We only support Postgres and MySQL now, but in the academic version, we've done Oracle, we've done Greenplum, we've done VectorWise. But the algorithm you use, so the Bayesian optimization algorithm or the deep neural network, that is the same. Because again, the models don't know, the algorithm doesn't care what a database is. It just sees numbers and you say, here's your objective function, optimize that. So we don't change the algorithm from one database to the next. What we do change is all the crap on the outside of it, of how to interact with the database system, how to determine whether we're making the right decisions. Again, constraining values, as they said, making sure that you don't turn off disk writes or other things that could cause safety issues. There's other challenges you face too then this is of like how to connect to the database, apply the changes and all that. And this is why we only support RDS right now, because they provide a standard API for us. And we don't have to worry about these things. So the example I like to use is like when we did an academic deployment of Ottertune at a bank in Paris. They were running Oracle, so we had to support Oracle. And there was all these weird corner cases of like the error messages from Oracle. It would crash at unknown times because we set knobs differently. It was such a huge pain, and RDS takes care of all of that for us. That we don't have to worry about it. Now we haven't tried Ottertune for Oracle RDS, but we just know that like all the crap we had to do for that for the bank, a lot of that we don't have to deal with, which is nice.
Yeah. What are some of the common problems or common optimizations that Ottertune ends up, recommending to different types of workloads? Or to rephrase, what are the common mistakes that people do when it comes to, writing queries or creating indexes or, provisioning in hardware? Like, what are the common mistakes that you see?
Yeah, let's go through all those. So for indexes, the common mistake we see is like people add way too many indexes, right? And oftentimes it's because there's multiple developers working on a project or an application, and this person's query runs slow, so they add an index. This other guy's their query runs slow, so they add another index. And before you know it, you got a bunch of overlapping indexes that are sort of unnecessary. And this because there's no sort of quality control. Like there's no DBA, or there's nobody saying like, okay, well, what do we actually really need for these indexes? So an example would be, you could have a table, you could have an index. Say you have 3 columns ABC. So someone will have an index on AB, and someone will have an index on ABC. Well, you actually can, the queries that need AB can use the index on ABC. If it's a B plus tree, you don't need C.
Yeah.
So there's things like that where like, this consolidation you can do. Because again, like the reason why this matters is because the indexes are going to sit in memory. So that's going to be taking up space in the buffer pool that you could be using to cache records, cache data, but now you're storing these redundant indexes. And then every single time you insert, update, or delete the table that has these indexes, you got to go also update those indexes, and that becomes expensive. So that's a common mistake we see. And actually, I think there's this paper from Microsoft, I think from 2020, for their automated index service on Azure. And they say that 88 to 90% of the recommendations that they generate are people to drop indexes because they have too many. And so that's why we sort of focus on that problem first. So I think that's the most common mistake people do. For query tuning, it's a whole slew of things, but I would say oftentimes the problem is not necessarily due to what the programmer actually did. So again, using join orders, for example. So you have a SQL query, select star from table foo, join on table bar. And in the way the join algorithms work is that the complexity or the runtime of the join will vary based on whether bar is first or foo is second, right? Like getting that join order is very tricky to do. And the reason why the optimizers can choke on this or get it wrong is because they don't have a full complete view of what actually your data looks like. So one way to handle this is make sure you update the statistics. So there's at least in Postgres, I think MySQL has it too. There's an analyze keyword that basically reads all your data and updates internal histograms to help the optimizer make these kind of decisions. And so for 2 table joins or 2 table queries, that's probably good enough. But when you start doing multiple table joins, then like the optimizer can get things really wrong, especially if you have wrong statistics. So in that case, the advice could be maybe try not to do as many joins, but of course that's not always possible. And this is where query plan hints could help. But again, to do that manually is a tough road. And something like Postgres, for example, doesn't have query plan enhanced by default. You have to install an extension to get that. So this is why I think automation is the right way to help in these things. Another common mistake we see is people have too many nested queries. And the challenge there is because the database system wants to try to rewrite. Again, I'm assuming your viewers run a nested query. You have a select statement, and then inside the from clause, you have another select statement. Or like a where clause has a select statement. And people can go like arbitrarily nest these things forever. And the right way to execute them is basically to pull out the nested queries, the subqueries, and rewrite the query using joins. But that's actually not easy to do. And Postgres and MySQL are pretty bad at it. Oracle's a little bit better. SQL Server is probably the best commercial version at this. The actually best data system that can do this is this thing called Umbra out of Germany, but it's like an academic prototype. DuckDB can do a little bit of this because they took the ideas from Umbra. And actually, my students sent a patch to fix how they do denesting lateral joins in the Spring. Like, so DuckDB is getting a little better at this too. But like, if you have a bunch of nested queries, the database system oftentimes just throws up its hand like, I can't handle this. So avoiding too many nested queries, I think, is another important thing to do. In terms of knob tuning, again, don't use the default configuration. Even if you're running on something like RDS or a managed service, we've had people tell us that like they thought Amazon was tuning the knobs for their database for them. And so it's sort of true. Like Amazon sets some default values that are better than like what you get if you download Postgres MySQL, run it locally on your laptop. But like they're not tuning it the way something like Ottertune can do. And even like something like PG Tune, Ottertune would do much better. So I clearly think machine learning is a better approach. So not using the default configuration would be the most obvious thing. For physical design, a lot of times in most cases, the schema is dictated by the ORM. And there are some things you can tune on the physical design for tables for using Postgres MySQL as an example. Like Postgres, you can change the fill factor for a table. I don't want to get in the weeds too much, but there's a parameter you can set for those things. In MySQL, you can enable things like whether you want the rows to be compressed or not. So there's some tuning you can do for that. But again, the major like rewrites of like unnesting denormalizing or splitting up tables or combining them back together, like that one is sort of a bit of an unsolved problem. And this is where humans, the machine learning stuff it hasn't really tackled that problem yet. But I think it's interesting. One of the things, at least on the research side, I'm interested in going into.
Yeah, those are very interesting points. I've been thinking about this, the gap of understanding of how databases work, because we don't have DBAs who help us writing queries, right? Like we are common developers who work on applications, have great product knowledge, have great, development experience, but not so great database understanding. So I was thinking of a use case. Maybe I don't know if it makes sense, but let's say I have a production workload and, I've been using something like Ottertune to tune my database. And this is a bit futuristic. I'm not sure if it's there yet, but let's say my workload is pretty stable and Ottertune knows my workload. And I admit that I don't have a great experience writing good queries, right? So can I use something like Ottertune in the future where I say, my workload, help me write this query, something like, ChatGPT. And could that be possible?
Do you mean like going from natural language to SQL?
Yes, but like, so something like, okay, the database I'm working with, the workload. I want to write this query, for example, or this is my query. Please optimize this query, something like that. So I'm more like I'm chatting with Ottertune, something like Chattertune.
Yes. So those are two separate things, right? There's one of like I say in English or whatever natural language I want to use. This is the answer I want. This is the query I want to run or write, and then there's some LLM, ChatGPT, or whatever you want to use, that then converts that natural language to SQL. So that is an active area of research now. We actually had a speaker from Alibaba talk about their recent VLDB paper on something called Cat SQL that can do this. And it's the key thing about that. What they do is like you have to inject like what the schema is into the as part of the prompt in the large language model. So it doesn't recommend, doesn't do joins incorrectly or doesn't hallucinate and pick tables that don't exist. So that's sort of one problem. I would say that most people don't write applications and you would not want to write applications in using natural language.
Yeah.
In that way. And I don't see ORMs being replaced by natural language, like for doing front end applications. Where what you're proposing is going to be helpful is, I think, on the back end, like business intelligence or decision support systems, like data warehouse queries, where you could have someone write, say in natural language, here's the query I want to write. And then something like ChatGPT could develop a first version of it. But then there could be like a dashboard tool or some user interface that allows them to refine that and check and see whether that is actually, is this the correct query they actually want. And the challenge is because there's so much impreciseness in natural languages, whereas SQL is debatable in some cases because of certain semantics, but it's a programming language. It's way more precise. So I see the large language models being used for OLAP stuff more than front end development stuff. And I think it'll just get better over time of like making sure they don't hallucinate or making sure that like it is, can convert whatever your natural language request is into the proper SQL query. I would say this is an old problem too. Like this goes back, people are trying to do natural language to natural language to SQL or other query languages since the 1970s. It's always been less than stellar results, and I think that large language models is a major breakthrough in that space. And then I think your second question was for a given SQL query that you do have, could Ottertune come back and say tell you how to optimize it, right? And I think yes. I mean, there was other people are sort of doing this now in a much better job than we are. Like there's EverSQL. They just got acquired by Ivan, but they were doing some kind of machine learning based approach to do SQL, Andy Pavlo checks, sort of similar to what Ottertune does now, but it's more sophisticated. I actually have a research project that I'm working on with my students back at the university, where we actually can take a SQL query and actually inject the correct query plan hints to do join orders, to pick access methods, pick whether you want, data materialized in memory or not. Like what basically we can tune everything that PG plan hints exposes to you in Postgres. So I foresee the future that we'll be able to do all the things that you'd want to do, but I actually don't think you need to have like a chat interface, right? Yeah. I think the real goal is just that the majority of application developers don't have to think about the database system. Yeah. Now, this is weird for someone whose whole, at least my academic and professional career has been like, okay, like databases are super cool. Let's build more of them. Let's people understand what's going on. But the ultimate goal, I think, should be the database system can manage all these things for you. So like, and you don't need to have a interactive experience with it to say, okay, now fix this, now fix that. The data system is, okay, whatever query you throw at me, I'm going to learn from it and just make it better over time. And just if you can ask it like, hey, what are you actually tuning? Why are you doing these things? That's great. But like, if really things should just be on autopilot and just do its own thing. And the question is, how much do you want the data system to be involved in, again, going up and down the stack? Like, should it be messing around with the hardware? Well, provisioning, sure, like you could do that. But there are other things you'd want to do with the hardware? I don't know. And then should you go now inject the self into the application code and say, okay, like I see you're writing the SQL query on your dev environment. That's going to cause problems in production. Here's how to actually fix it before you actually commit anything and submit the PR, merge it. So like I think that would be the next stage after you have full automation on the data system itself. You go up the application stack and you make it better for people. You essentially prevent people from doing stupid things before they can do it.
Yeah, that makes sense. And thanks for answering the imaginary question that I had. I guess you have mentioned a bit about the current limitations and, the future, kind of the roadmap or things that you've been working on. But what's more in the future in this database optimization domain?
So I think as I said in the beginning, most of the 4 areas of tuning, right? So the physical design, knob tuning, index or query tuning, and then sort of hardware resource provisioning. Most of the work has been done in the first three. There's a ton of papers on index tuning, partitioning, key selection, knob tuning. Obviously, there's a lot of this. More recently, there's a lot of work in this space. I think Ottertune set off a. I mean, it's not to say people haven't tried what Ottertune has done before, but like Ottertune was the sort of the one of the first of a new cohort of people working in this space, applying machine learning to knob tuning. And then query tuning, there's a little bit more work in this space, with myself and then others. I think that I think hardware provisioning is as an important unsolved problems. And then this is more in the research side of things and not Ottertune. I think the next level is going to be sort of holistic tuning. And so think of like something like Ottertune right now, it has its models for query tuning, it has separate things for index tuning, it has separate things for query tuning. And they don't really talk to each other. Or they don't consider the implications, the impact of tuning one as it relates to another one. And the reason why no one has sort of looked at doing this holistically is because the problem space is massive, right? I mean, just picking what index to choose, I mean, that's been known to be an NP hard problem, for decades. So now if you want to say, okay, all these things you want to tune all at once, how do you handle that? And then the challenge with this one is that if the schema changes, like how does that affect that? I'm not going to the machine learning stuff too much. Like if the schema changes, does that break all your models? Because now the dimensionality changes. Like if all of a sudden, if I add a table, can I reuse all the training data that I've generated before to do all this holistic tuning? Because now the feature vector might change. So I think the big one of the big things we're actually looking at is, again, how to tune everything all at once. And the preliminary results are actually very promising, that you can do much better than just tuning, a little bit here, a little bit there, like piecemeal or incrementally. Just do it all at once. And then the next big thing we also think is going to matter is going back to you were saying before about these known periodic spikes that are on a calendar. Can you start infusing in the models to be able to say, okay, I know that there's some event in the future that I have to prepare for, so let me start tuning now. So an example that you said is like, if people know Black Friday is coming up, so like a month before, they're like stress testing, and maybe they're scaling things and just re-replicas. The example I always like to use with this was the early days of like the MultiB H2O project. We went to go visit PayPal. And what they told us is like they were freaking out, for every Black Friday, like leading up to it, because they know that it was going to stress their giant Oracle database. So they would start manually moving off data off that Oracle database, put on sort of side databases, because they know that that their one database instance was going to get hammered. And so if you now know that like within a year, okay, I'm gonna have this event coming up, can the system start preparing ahead of time? Or another example would be, I know that at 8 a.m., or 9 a.m., the stock market is going to open, and I start doing a lot of writes. So like at midnight, let me start building indexes in anticipation of that morning workload, right? So if you can start learning these patterns and then have preparation happen well before you actually need it, I think I would say if we could achieve that by the end of the decade, that would be amazing.
Awesome.
And I think that would be that's sort of the last piece of what how humans are managing databases now. Like, again, we can pick indexes, we do knob tuning better than humans can, but like it's understanding the big picture of how this application is going to interact with the database over longer periods of time. The joke I like to say is like, I want to build a database system that will live longer than you. You'll be dead as long as your credit card can still pay Amazon or Google or whoever your cloud provider is. Like it just runs forever. That's the dream.
Yeah, that makes sense. I am really looking forward to, the future inventions and, future things that are going to happen in the database world. Unfortunately, in the interest of time, we have to, end this amazing session. But it was really insightful. It was, really, a lot of value. I'm sure people are going to get a lot of value from understanding how tuning works, what tuning means, and why it is important. For our viewers, if you want to learn more about database tuning, I think there is a great blog by Ottertune. So please do check it out. Also, do check it out, Ottertune, what kind of optimizations it does, and if it makes sense for your workload as well. So yeah, thanks a lot, Andy, for joining me today and discussing and answering my questions. I am really looking forward to releasing this episode and also doing more collaboration on database topics with you in the future.
Yeah, thanks, Evan. It's fantastic.